All right, so welcome to COP5615, right? So this is a distributed systems class. For those of you who don't know, I'm Alin Dobra. I'm a faculty in the CIC department. My main specialty is databases, but I do dabble in distributed systems. I'm going to mention some of the work I have done. But nevertheless, I'm very excited about teaching this class, mostly because I believe it's one of the most relevant classes you can take in this day and age, because distributed systems are about everywhere. So let's try to run a survey. Which of you has a smartphone? Yeah, many computers, as my wife says, right? So distributed systems all the way. I mean, it's unbelievable how much of distributed systems you have in your pocket. Make sure it's on vibrate or off, right, for the class, so we don't get bothered by applications of distributed systems. All right, so on the web page, which is very fresh, because I put it up only this morning, you have the information about me, the room where I'm going to have the office hours. Tentative office hours are Wednesday, 1 to 3, right? This is my cell phone number. If nothing else works, this is what you can call. Please don't call after 8 p.m., all right? I have relatively small kids that need to go to bed, so. And my wife gets very annoyed if I get calls after 8 p.m. But other than that, it's fine. I'll deal with it. Okay. Now, you know when the class is, right? To Thursday, 8:30 to 10:25, and Tuesday, I'm sorry, and Thursday, just 1 hour, 8:30 to 9:20. Here, all right. Sorry, too much traffic. Okay, the traffic kills me. It's people moving around. I lost my train of thought. Okay, website is up. You can look at this kind of information. Let me give you some idea of what I expect in this class, which is probably a much more interesting topic. Okay. So let me start first with some broad principles. I'm going to go today through some introduction, what distributed systems are. But let me tell you what I want to achieve in this class. Okay, and that's going to be the guiding principle throughout the class, and it's going to set up my expectations, right? I'm a true believer in hands-on experience. If you don't build things, you don't learn things. Okay. Now, to this end, I am also a big believer in don't test through exams, because they're not that relevant. I mean, I could kill you with exams and give you very tricky problems and so on, but that's not really what's going to help you in real life. So this is why the focus in essentially both the classes that I teach in each of the semesters, the focus is on large projects, okay? So to that extent, your grade essentially is going to be determined 70% by projects in the class and 30% by quizzes that I administer every week. No exams, no midterm, no final. You show me your final project, you're good to go, okay? Now, that doesn't mean this is an easy class, or it doesn't mean that this is a low load class. Okay? I will give you projects that require you to think, and I will give you projects that require you to do a lot of work and learn a lot of things. And I'm going to go into details what exactly those are. So to a large extent, we are going to plow through important topics in distributed systems, and you're literally going to write a program that does what I say in class you should do. Now, the purpose of the quizzes, and this is all in the syllabus, the purpose of the quizzes is really to make sure you follow what I say in class. I mean, literally, your buffer needs to be only about a week long, right? Usually, the videos that you can access online that are being shot as part of the Edge course, right, are very helpful to go back over the material and see what is it that I've been saying and so on. Now, I've been told by students like you that, and this is not the case now, but trust me, it's going to get like this. I talk fast, and I really talk very fast. Okay. Now, that's where videos come into play. I've heard some people watching the videos minimum 2, 3, 4 times, right? But also, this is where you come into play if you show up in class. You have to, your goal in class is to slow me down. You have to slow me down with questions. You have to slow me down with interesting things you say, and so on and so forth, right? You don't slow me down, I will cram in a lot of stuff in. Okay, I mean, a lot of stuff in. Now, To a large extent, my classes are never really only about the topic I'm teaching, but broader context issues in computer science and bigger things, right? So I will tend to give you a lot of ideas of how distributed systems fit into the big scheme of computer science education and engineering education in general. Also tell you the difference in thinking between different areas, and I do this in the, for example, database implementation class as well, right? So I'm going to say, okay, so let's put a theoretician hat, big O notation, what happens here? Okay, let's put a hacker hat, or let's put a distributed systems hat and see what the issues are, how things go on and so forth. This is a very healthy exercise. Try to think like each of independent areas, and this is, to me personally, the secret to get under the skin of various ways of thinking and to accomplish things, right? Changing the point of view, changing the way you think will fundamentally open up new opportunities, right? Some of the biggest breakthroughs come from the fact that somebody thought with a different hat on, right? So I'll point out things in which I'm going to say, hey, distributed systems people say this, but really database people say this, and theoreticians say this. And they're all interesting points of view, okay? So you're going to see quite a lot of that as well. Now, even before going into what distributed systems are and whatnot, let me tell you what language we are going to use for all the projects and why am I doing this. I'm going to try to give you a bigger introduction Tuesday when I have 2 hours, because I want to give you an introduction to distributed systems, okay? So let me run a little survey. How many of you heard of Scala? Okay, so what's Scala? Well, it's probably a programming language, because I just talked about programming languages, but why would I bother to introduce you to another programming language? I mean, why learn more than one language? So how many of you, I always like to ask this question, maybe my favorite question. How many of you, after learning C, had the feeling you can do anything? Right? If you learn C, you say, wow, I can make computers do stuff. I can build anything. So why do we have any more languages than C?
C is hard to write.
But why is C hard to write? What makes C hard to write? By the way, these are fundamental questions that a lot of people don't ever ask. So why would it be easier to write something in another language? Well, I'm sorry? Why would debugging be easier? Yes? If you get what? Well, so it turns out that, well, so let me just say something interesting. Almost all programming languages nowadays are in fact implemented in C. So to some extent, everything you write eventually makes its way to C, right? So it's C. At the bottom, it's C. There's no question about it. It's C or C++. Now people switch to the more object-oriented version, right? But this question is fundamentally related to something else, and it's called abstraction. So what I'm going to be doing throughout the class is point out the need for the right abstraction. If you have the right abstraction, your job is easily an order, possibly 2 orders of magnitude better, right? And I selected Scala as a programming language because of the abstraction it provides for something like a distributed systems class. Okay? Now, let me make some kind of a comparison. I want you to understand why we're not doing things in C and C++. A lot of these classes here, yeah, do some kind of network connection in C and C++ or whatever. I'm not doing this because using Scala, you're going to be able to code easily 10 times faster, which means you're going to easily do things 10 times more complicated. So at the end of the class, you would have implemented things that in C would have taken, each small project would have taken the entire semester to do it in C. Okay? And also, I want you to get a taste of how the good life is when it comes to coding things. To a large extent, you're taught the wrong paradigm, right? Now, by the way, I'm a really good C++ programmer. I'm gonna, if you don't believe me, see the database implementation class, and I really know what I'm talking about. But C is almost always the wrong language to do something interesting in. Okay, so nowadays I find myself running away from C as fast as I can. Now, to do the core of a database engine, you still have to use something like C or C++. But something else interesting happens, and this is why I want you to be exposed to Scala. Let's suppose you join a project, and the designers of the project decided to do C and not Scala. What use is Scala for that? Well, so here is what I've actually done for my own database engine. You can use high-level concepts that show up in Scala that you're going to be exposed to implement certain features in C to make your life easier. Debugging is very hard in C because you have not built the correct gadgets to help you do things. So a lot of the stuff that I'm going to talk about in Scala, in particular the actor model, which I'm going to explain a little bit today, can actually be implemented as an abstraction in C or C++, and I have done so. And my entire database engine is based on this high-level actor model that, in fact, is in Scala. Now, you would think that I first learned Scala and then implemented the actor model. Well, it turns out that it was the other way around, but it doesn't matter. For you, this is going to be very important. Knowing Scala will indicate what abstractions to customize for that C application you're writing so that you can actually stay high level. All right? And to a large extent, a lot of languages, Python, JavaScript, and all the other ones, right? It's some kind of a high-level abstraction on top of the raw base that's actually written in C or C++. Now, it turns out that Scala is not written in C. Maybe it should be written in C, at least the core language, because it tends to be quite lazy when it comes to compilation. It's written in Java. Of course, the question is, what's Java written in? Well, in C, really, okay, or C++. What's C written in? Well, C is written in C. They managed to bootstrap the compiler, so that's a done deal, okay. A lot of the C and C++ compilers now can, actually the GCC, right, the C and C++ compiler is really written in C, not in C++, okay. All right, so Scala, it's a modern language, has been introduced in 2002, has some of the best ideas from the languages community, and has something that I believe it's invaluable, which is this actor model, okay. I'm going to be talking about actor model up and down throughout the class. And how many of you heard about the actor model, by the way? What's this actor model? How many of you heard about threading and multi-threading and threading libraries? And come on, you must have done some kind of parallel computing distribution. I mean, a little bit of something, right? Fire up 3 threads to do some job. Well, it turns out that threads are a really bad abstraction. Okay? They look OK on the surface because you can get a little bit of work done, but once you reach a certain level of complexity, they're impossible to control. Right? Now, just to give you an idea, the actor model has been proven to millions of actors. By the way, an actor is some sort of a very fancy thread. Okay? I can even give you an idea what an actor is. Right? It's an independent entity that runs potentially in its own thread of execution that exchanges messages with other actors to get stuff done. Right? How do threads communicate? I'm going to go through this in the class. How do threads communicate? In any language you want, I don't care. Right, shared memory, right? Well, 1 second. That's inter-process communication, and it's threads running on different machines that do message passing. How many of you has used message passing on 2 threads that run within a single application with no network access? I don't think you use that. Well, it turns out that if you implement the actor model, you have to use some sort of message passing, right? So to some extent, you take a lot away from the thread model by saying, don't do this and don't do this and don't do this. In particular, do not communicate through shared memory, okay? I'm going to come back to this. And you say you must communicate through messaging, and you immediately say, hey, whoa, 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 that's less flexible, which means you're throwing things away. Well, it's less flexible maybe from an absolute point of view, but it shapes the way you write the program, and you're going to get much more complex programs written in the proper way. Not to mention that debugging is much easier, and in fact, you're going to do a debugger yourself, okay? Because we're going to get to this distributed debuggers. So if you think debugging a single-threaded program is hard, or even a somewhat multi-threaded program, try debugging many programs that, through a distributed systems kind of architecture and approaches, talk to each other from multiple machines. Now, how do you debug that? Well, that's why a lot of stuff doesn't quite work, right? Because those debuggers are hard to come by. But you're going to write one as part of this class. This was one of the most successful projects I had last year, right? A distributed debugger. Now, a distributed debugger for threads, it's a really awful thing. But for actors, it's going to be relatively straightforward. I'm going to talk about that. So here is what I want you to do the moment the class is over. You can even, as you walk up the hill, pick up your phone and start looking into Scala. Right? I will give you some idea what Scala is. I'm not going to spend more than, let's say, a lecture on it, or maybe even less. You're all grown-ups, right? Go and start and learn. This is a new language. I will point out certain pitfalls, and I will explain the actor model, because it's very important that you get it right. Now, when it comes to languages, right, Scala is many things in one, but I would strongly advise you to go more towards the functional programming side. Okay? So it turns out that Scala designers tried to fix some of the problems. I mean, it depends on what you consider to be a problem, but try to fix some of the problems other languages had. Scala is, for example, heavily influenced by ML. How many of you heard about ML? Or a modern version is OCaml, okay, OCML, okay? Well, the problem ML had is the fact that it was too snobbish. Okay? It was written by very sophisticated type theorists, language designers. And it only catered to very sophisticated language designers, which means it had all of these extremely fancy functional programming features to the point that normal programmers were going mad with it. Right? Don't get me wrong, very, very fancy, extremely advanced stuff, but only in a certain category. Even writing something like a for loop sometimes was hard. Believe me, there are languages in which it's hard to write a for loop. So to compensate for this, the Scala designer decided from the get-go that they want to cater to both the imperative world, C, C++-like languages, and the functional world. Okay? That doesn't mean you should not use, in a heavy way, the functional part. It can do a certain magic that's very hard to express otherwise in an imperative way. I'll give you some examples, okay, when I talk about Scala a little bit. Right? So do take the time, if you have not exposed yourself in a significant way to functional programming languages, to program in a functional programming way in Scala. Your programs are going to be much more compact, much easier to debug, or just free of bugs, essentially, okay, except maybe some minor logical stuff. Okay? Now, Scala is implemented on top of the Java virtual machine and can actually make heavy use of Java libraries, which means anything that's available in Java, it's actually available in Scala, plus a lot of goodies that are only Scala. Okay? Now, strangely enough, on portions, Scala is faster than Java. Now, how is that possible? It's implemented on top of the same technology, and suddenly it's faster than the other language. What gives there? By the way, one thing that I'll try to instill in you in this class is to question everything, including everything I say, but everything you see. So how is it possible that a language is faster than another one, even though it kind of piggybacks on the previous language? I'm sorry? So what's compile time? What does compile time mean?
First, the code is breaking into parsers and every statement.
No, but I mean, essentially they use the same technology, right? They do some kind of compilation. They compile against the Java virtual machine, so it's the Java bytecode, and then you run the Java bytecode. So why would it be faster on portions? Well, it's really all in the compiler. It's what is it that you generate. This is why some C compilers are much faster than other C compilers. Or if you put certain options to a C compiler, it's much faster than another compiler. So what is actually happening in Scala is more than this. What's happening is, because Scala has the right abstraction, they can see optimizations that are very hard to see at the level of a pure imperative language. Okay? So Scala then picks up speed by just this is something interesting, in fact. If you're forced to program against a certain interface, you're forced as a programmer to reveal structure that can actually be used for optimization. That one of the tragedies with imperative programming, and C is the biggest culprit of them all, is that it's too easy to dizzy up the compiler. I mean, literally, you can almost anything you write in C, the compiler is not going to guess exactly what is it that you're doing. There's so much variation, right? So for example, even things like implement a hash or implement a linked list or whatever, right? Everybody's going to do it slightly differently. The compiler can't really tell that, oh, yes, I know this is a linked list implementation. Or even other things, for example, sorting, right? It says, oh, I know. You're doing sorting, but you have an inefficient sorting because you implemented bubble sort. I'll replace it by quick sort, and everything is going to be so good. Now, that's a fantastic compiler, but it doesn't exist at the level of imperative languages. As opposed to restricted languages, right, where you can just say sort, Actually, in Java, and that's the case also in Scala, it's very hard to implement your own hash because of the kind of special manipulation that needs to be done with references and non-references and so on. And that essentially means that the particular data structure that's provided is, in fact, fine-tuned. So if your use matches the intended use, it will actually run fast. Okay? And that's true, by the way, for Python or JavaScript or whatnot. Right? So start learning Scala. It's definitely a very cool language. And most important to me, it has this actor model built in. Actually, it has 2 actor model frameworks. And we are already going to switch to the better one because there is a commercial company, it's called Akka, that's doing this better actor model in Scala. And Akka has an extremely aggressive actor model. You can actually have up to 10 million actors because they're extremely efficient. And they can pass up to 10 million messages per second between actors. So it's extremely fine-tuned machinery to do this kind of actors, right? So just to give you a very, very quick idea, right, what these actors, I mean, the nice thing about actors, this is what the name suggests also, is it mimics kind of what's happening in real life. You're trying to completely isolate who does what, right? So for example, let's say you want to carry out computation on multiple CPUs. What you can do with the actor model is say, you know what, I'm going to make an actor responsible for each of the CPUs, and I'm going to make a boss for the actors that distributes the work. And then you're going to, by the way, this is going to be your first assignment. And then in a natural way, you, in fact, have a very good solution to the problem. And I'll explain in class why this is a very good solution. Then it's very easy to think about what's going on in the system. You're just looking at the messages passed between the actors and who does what. So each of the actors can do some real work by running computation and can exchange messages. That's going to limit of who sees what, right? So another kind of strategy we are going to have is if another actor needs a certain resource, you can give the actor the resource, as in I don't keep it so then I don't have conflicts, right? I'm going to talk much more extensively about this kind of strategies in the database implementation class. OK, so let's not go more into Scala. Start reading it. I have a link here. And hey, Google is your friend. So just Google Scala. A large amount of code out there. I would strongly encourage you to see how other people write the code, right? And get going, because I'm going to throw the first assignment at you and say you have to do it in Scala. And then you have to learn it. OK? Good. Now, grading, this is my updated graded kind of scheme. Right, 93 to 100 is going to be A, and then proportionally down to E. Right? Now, let me say something which I think is very important. I do not mind giving everybody an A in this class. And in fact, grades tend to be good in my classes. Okay? But I do want to see that you're working at the right level. So we're not going to do any curving on any of that stuff. Okay? I believe each of you can become good in your own right. So that should be your target, the A. I do very well on the projects. I'm still going to have some bonus projects on top of the regular stuff, at least every now and then. And do take those quizzes. Right? The quizzes are going to be just multiple choice. Every now and then I'm going to have maybe, OK, describe this or do this. Okay? Just to make sure that you don't write a script to take the quiz. Right? But it's not impossible. Okay, and I'm not going to play games in which I try only the best people get whatever grade and so on and so forth. Okay. Now, I do have warnings there, right? Things like, hey, you're going to do a lot of programming. It's not so much how much code you write, it's how much you have to think. And what I'm going to do is strongly encourage you to think, especially in Scala. Thinking is paramount, right? You're not going to do the kind of things you have in C, in which you keep on writing, and you end up with 10,000 lines of code in a jiffy, right? A lot of the assignments or a lot of the projects might have 100 lines of code solution or less. But the trick is to have the right 100 lines there, right? So don't really dismiss that. Now, textbook. I switched from last year because I think this is slightly better textbook. This is Distributed Systems, Principle and Paradigms, Tannenbaum and Van Steen. To some extent, it doesn't quite matter, right? Because I'm going to be teaching the material in class. The quizzes are going to be about what do I teach in class. The projects are going to be anyway reasonably open-ended. Google is your friend, but not the previous projects that other students did. I'm going to change them slightly anyway. to a large extent, what I ask you to do in this class, it's so new and so fresh, Googling won't really help you, right? Which is very good. And when it comes to this fresh, let me give you some idea of, one other reason why I picked Scala. Okay. So how many of you know about Twitter? Or how many of you don't know about Twitter? Okay. All right, so what does Twitter do? Forget about the new video application. We are going to talk about something like that also. But Twitter, well, Twitter just distributes tweets, right? So if somebody tweets here, you look at who's signed up for the tweet, and you have to put them in whatever their inboxes are. Okay. Now, the original Twitter application was essentially written in some sort of a C combined with PHP and whatever else was in there, right? Sorry?
Ruby on Rails?
Sorry, Ruby on Rails. That doesn't make it much better, right? Now, don't get me wrong. Ruby on Rails, it's a great platform, but not when it comes to doing this little tweets, okay? And I will talk about those strategies because they turn out to be very, very important. It's how do you deal with a large number of clients, for example? What architecture do you use, so on and so forth. So what happened, and I think this was in about 2009, 2010, a group of 4 people inside Twitter excited about Scala because Scala got to the point where it got to be interesting, and excited about the Akka actors on top of it. In 3 weeks, rewrote the entire Twitter engine, okay? In Scala, just 4 people, 3 weeks. At the end of these 3 weeks, the engine was 10 times faster. Now, is that possible? Well, it's really not the case that Ruby is not fast. It's the right abstraction, and you're going to see this, because all you need to do is put these actors, and sending a tweet is basically sending messages between actors. And hey, I already told you that on your laptop you can do easily 2 million messages per second, so, right? That's a lot of tweets that could be covered. Remember, Twitter has a lot more money and much larger data centers, okay? A nice thing about Scala is the fact that in a very straightforward way, you can send messages within the same machine or remotely to other machines, and it's very nicely abstracted away. And this is really the core of this idea that we are going to do abstraction. And by the way, distributed systems are a lot about abstractions, and I want to go at least quickly through those kind of things. Now, do take the time to read the syllabus. It's reasonably straightforward. It's basically what I said. Now, this is very tentative. Okay, I do like the freedom to change what is it that I teach, depending on how the class reacts and so on. It's going to be all the important topics, but I might throw in some cool stuff here and there, right? We'll take examples, ask things like, how does Gmail work? How does Gmail work? Well, you point the browser to gmail.com and it works, right? Well, okay. So we've been talking about many, many, many things. And you probably already know. Distributed systems are absolutely everywhere. I just argued before the class started that they are in your smartphone, right? They're always behind the scenes, right? So let me go through some of the slides. I'll try to use as much as possible the slides that the textbook writers have. Okay, so let's see what's in those slides. Okay. Chapter 1 first. Okay. So this is. So very quickly, we have about 20 minutes. I'll run quickly through this because this is really just high-level fluffy stuff, okay? So whenever a research area has a problem defining what is it that they are all about, you know that things are weird. And distributed systems people had, for a very long time, trouble saying, what are distributed systems, right? Now, to a large extent, and this is what I'm arguing even more in the database implementation class, you have to treat even a single system as a distributed system because it's a much healthier paradigm to build on, right? So for example, how many of you have any idea how many cores you can squeeze now in a single chip, in a single processor?
At least 64.
Well, who does 64 now?
There was a startup doing Parallella, which gets like 64.
Yeah, right, but let's call that exotic. Let's do more mainstream stuff. Yeah, so there are a bunch of MIT groups that worked on that, and they're trying to squeeze in combinations of ARM-like processors and put 64 in a chip. Yes, 64, but that's still a little bit expensive. But let me give you a shocking number. $500 buys a 16-core processor right now, each core running at 1.9 gigahertz, right? Usually what I tell people is if your machine doesn't have at least 8 cores, maybe you should buy another computer. Or laptops are fine at 4 cores, right? So how many people don't have at least 4 cores on their phone? Well, the new phones have, all of them have at least 2 cores, right? If the phones have 2 cores, you have to start to be worried about what this core stuff is all about. And what I'll strongly argue in class is the way to program multi-cores is, in fact, using distributed system principles. And distributed systems technology, things like Scala. Okay, you're going to get a lot more mileage out of it. Anyway, definition of distributed systems, collection of independent computers that appears to its users as a single coherent system. Well, we'll see about that. Okay, it never really looks very coherent, and we are gonna talk extensively about this. Now, let me give you a little bit of a history and background, and I like to do this quite a lot. History is very important because you can see the thought process, how people got to a certain point. Okay, the distributed systems classes before and material before, and by the way, that includes Mr. Andrew Tannenbaum. Okay, was really about designing distributed operating systems. So the rage 10 years ago, 15 years ago was distributed operating systems. Tannenbaum designed a system. So how many of you know about the history of Linux? What was the project that inspired Linux? Minix. Who designed Minix? Tannenbaum, right? So Tannenbaum designed Minix when Linus Torvalds was a student, and Linus Torvalds was hovering about in that same area, right? And Minix was designed to be an educational operating system for students in the class to get hands-on experience how you design an operating system. Now the follow-up then, right, Torvalds used Minix to bootstrap Linux, and then Linux became independent, and a pet project became one of the biggest phenomena in modern software engineering, right? But Tannenbaum moved on and started designing Amoeba that was a distributed operating system. So now suddenly, if you look at this slide, you see local OS, local OS, local OS, local OS, and distributed system layer, middleware. So what happened? Well, what happened is people realized that you don't need to plug this stuff deep into the operating system to make it a distributed operating system, like Tannenbaum wanted to do, in which the transparency or whatever you're trying to achieve there, it's just done. You better do it in the middleware. It's a lot more flexibility, right? And it keeps things sane. So for the most part, pure distributed operating systems are non-existent, are dead. What you have is very good local operating systems with very good networking on top of it, on top of which, through many layers, you have this middleware that allows you to do the distributed system part. So to a local extent, these things still look like local machines. And they can be dealt with as local machines, and also supposedly as some sort of a distributed system. Okay? So fine, what's a distributed system supposed to do? And this is, by the way, an ISO definition in 1995, the International Standardization Office. Okay? These people really like fancy names and fancy descriptions, and they came up with some sort of a standardization for almost anything. Right? And these are the, let's see, 6, 7 types of properties that you would require a distributed system to have. And in the end, you can't really have all of them, but that's a different story. Right? And I just want to point them out. I'm going to come back to this over and over and over again. But the thing to keep in mind is you're not trying all aspects of that combination of machines to have these properties, just the high-level application. That's enough. Right? So when your phone is accessing, let's say, Gmail, you don't really care that the almost million machines that run the Google right now, right, they can be accessed as independent machines as well. All you care about is you just go to gmail.com or whatever and you get your email, and that's it. Okay? So all of these properties are related to transparency. And transparency is really about hiding. It's pretending that things happen in a certain way, but in fact they happen in another way. And by the way, this transparency is pervasive throughout anything that means technology. Right? Let me just give you a simple idea. For example, hard drives. How do you access a hard drive in Windows, let's say? Well, they correspond to those, whatever the drives are, C drive or whatever. But, I mean, did you ever ask yourself, what exactly does it mean to get information from a hard drive? I mean, somebody must implement that C drive. So what's happening is we have many layers in which we have logical names corresponding to some more physical things. But it turns out that what looks physical at one level, it's actually logical for a deeper level and deeper level and deeper level. At some point, you get to transistors and bits on a wire, right? But we're not talking about a single step. You're talking about a stack of these steps, and usually probably at least 7. We're going to talk about what happens as you get closer and closer and closer to the wire. So why are we not directly talking about what's on the wire? Again, abstraction. You go insane if you think directly about what's happening in the wire. You're trying to make your life easy by using higher and higher and higher level abstractions, right? So the kind of transparency you're mostly used to is access transparency. You have a logical name for what the physical device is, and that happens absolutely everywhere, including on forget about distributed systems, happens on all the systems, right? For example, in Linux, the way to talk at the lowest level with the operating system about the device is to give it the major and the minor number. But that itself, it's not really hardware. That itself, it's a logical abstraction. So it's transparency over transparency over transparency. And everybody knows a little bit more about how things are, right? So access transparency is high differences in data representation and how resources are accessed, right? The URLs are kind of the ultimate if you want access transparency. Location, hide where resource is located. Right? Dropbox. How many of you use Dropbox? Good, because it's a pretty good product. Yes, great. Dropbox on almost all operating systems allow you to access the Dropbox as a local drive. Now, how is that possible? Well, again, it's some form of location transparency. But actually, combine access and location transparency. Once you get that Dropbox daemon or whatever it is running, it does all the magic to hide where the data actually resides. And by the way, it doesn't reside necessarily at Dropbox.com because that, do you know actually how Dropbox stores stuff and what do they do and how they do it? Do you know the technology underneath? They're reselling you Amazon services, right? So Amazon has a storage service, and Dropbox uses Amazon storage service, which itself provides its own transparency layer, and put their stuff on top, and then the daemon puts more, and there is a lot more on the Amazon services, okay? So even the big guys use other big guys to sell you stuff and give you things. All right. Now, it gets harder as we go down the list. Right? So migration, hide that the resource might move to another location. This is extremely important when it comes to modern distributed systems. Right? You go to, for example, I made the trip in Romania. Right? I can still go to google.com. I mean, right? But I get some kind of a Romanian news and Romanian stuff, right? So that's potentially some kind of migration. Relocation, this is related to migration, right? So a resource may be moved to another location, but while in use. One example of this is, for example, if you access the internet from your phone and you move through the campus and you use the wireless access, you actually get switched between wireless access points. Actually, even if you sit here, I already see 2 wireless access points, right? So depending on which part of the room you are, you might actually get passed to another wireless access point. And that's, in fact, a relocation transparency. You don't care at the application level when you're browsing the web what is the wireless access point that it's allowing you to connect to the internet, right? Things are not always as nice as the wireless access points, though, okay? Replication. This is extremely important because otherwise, things get lost, right? And now, Gmail can put your data on ultimately a single hard drive somewhere. So they have a million machines. Each of them usually have about 4 hard drives plus an SSD. So you're talking about 4 million hard drives. Your data resides on one of those 4 million hard drives. That's not good. Hard drives keep on going up and down. You would be upset, even though Gmail, technically, it's a free service. You would be very upset if they lose your mail, right? Any of your mail. So that's not good. Even though some services, and you can notice this, I noticed this on Flickr, every now and then give up on this will make your data available. So every now and then, your pictures get this nice icon that says your picture is temporarily unavailable, which means Flickr has some issues with replication, right? So we already know who's doing a good job and who's not doing a good job. OK. Concurrency. This is simultaneous access to the same resource. It's extremely important when it comes to especially something else called transactions. Okay? And in particular, you want to hide the fact that other people, other systems are using the same resource at the same time. Now, why would you hide that? Because if you don't, you create an extremely hard to deal with abstraction. right? So imagine, for example, that I would say, hey, you can go at an ATM and do transactions on the, do something with the ATM, put your card in, get money, move it. But if it just happens that somebody else accesses the same account, then all bets are off and we can't tell you what happens. Now, would you be happy about it? No, right? You would say, whoa, whoa, whoa. You mean every now and then I have unexpected behavior, right? So, if it's in your favor, it's fine, right? Like Monopoly, bank error in your favor, that almost never happens, right? It's the other way around, right? So it becomes extremely important. And it's, again, all about abstraction, because any kind of transparency provide some sort of an abstraction isolation. So concurrency transparency means you can think about the system as belonging to you, and you're the only one using it, but in fact, many other users use it, but will do the magic to keep that simple abstraction going, right? That's called transaction processing, and I'm going to talk extensively about it, because it turns out to be very hard to implement. So all of these transparencies provide extremely useful abstractions in the end, right? Failure. Now, this is probably the best of them all, right? High failure and recovery of a resource, okay? More work has been done on failure in distributed systems than probably all the other things combined, because it's so crucial, right? How many of you heard about the fact that all Google services were down for between 2 and 5 minutes? Literally the whole world knew, right? The question people had is, how is this possible? Google is not supposed to go down. Why? Well, most of the time they have a nice failure transparency implemented in there. So don't get me wrong. Google machines go down all the time. Actually, they go down at really high pace. And I'm going to give you later ideas of how bad it is. And might not be a complete failure, and that's the problem. Okay? You might have these transient failures in which simply a machine decides to doze off for a couple of minutes just because, right? Or you even have rats that chew on the wire, right? You have all kinds of things when you have a large data center, okay? Thunder and disrupt something, all kinds of things. So dealing with failures and providing some sort of a failure transparency, it's almost kind of the center point of distributed systems. Achieving that kind of allows you to have a great distributed system. And we are going to talk extensively about, especially about the failure. Okay? But having failure, obviously, is very, very nice. For example, the main database goes down, but somebody picks up immediately, right? Some kind of hot spare, a failover mechanism. Then it's great. You might not have any disruption in service. So let's talk about physical failure. How would you deal with this, right? So by the way, physical failure is extremely important in a data center. So you have a data center, nice machines and everything. You serve web stuff. And then a GRU decides to cut down the power, right? Or you have a big storm or something and cuts down the power. So how would you ensure failure recovery there? Well, this is why we have generators. But then there is a problem, right? So for example, even GRU has a data center, by the way, in town. If you need to set up a nice server, it's reasonably priced. But the GRU people, I talked to them, and they said, hey, we have a generator that kicks in 6 seconds. Okay? But what do you do 6 seconds? Right. So you already see that even to deal with some sort of a physical failure under things like power goes down and so on, you need to worry about these things, right? But when it comes to operating system running amok and so on, it's not going to be as easy as this, right? This is why failure is hard in general, and it needs to be thought out throughout the system, okay? So then, did Google not have a backup for their system and generators for their data center? By the way, Google has many data centers. Don't even have one data center. In the data center, everything is redundant. They actually have their own power plant in some of those data centers, right? All that good stuff. So how did all the Google services go down? Well, we still don't know yet, but we can speculate. The trouble is, and this is a crucial thing that we are going to tackle throughout the class, it's single point of failure. The Google must have had a single point of failure somewhere. So a lot of the work in distributed systems is and was about making sure you don't have a single point of failure. It's very likely, by the way, that a single point of failure was something extremely high level, for example, at DNS mapping or something like this, right? Or some misconfiguration between the routers in the data center that dizzied up things or something like that. So it's really the very entry point that you don't even think it exists, right? One of the things we would have to talk about in class in the context of distributed systems, and it's really the bigger context, is security, some form of security. Because, you see, all of this transparency stuff, it's things that users get to expect and get to be annoyed about if they're not provided. Okay? So I believe Amazon was down for a few hours. So these guys are losing $1 million an hour when the website is down, at least. So downtime costs money, and this is a very real thing. Now, Google, hey, it was 2 minutes, 5 minutes. People were, actually, apparently, some of the stories were, people tried to Google, it was down, and they said, now what? Nobody knew what to do because everybody depends on Google to get their stuff done, right? So thanks God it was just a few minutes. But more than a few minutes, it starts to become very expensive, which means there is the counterpart, namely, there is a big incentive for hackers to try to take down such systems, right, in order to inflict some sort of damage, to make some sort of point, money, or combination, or whatnot. Right? How many of you heard about this guy, I think from Palestine, that submitted a bug report for Facebook, right? Those guys ignored him, and then he exploited the problem he discovered to put something on Mike Zuckerberg's website. And then Facebook got annoyed, right? So, well, apparently hacker community puts together money to pay the guy because Facebook is not doing the right stuff. All right. But a lot of these kinds of transparency can actually be attacked, right? And a classic example is 2001 when eBay was up and down over a week, annoyed many, many people because that's when there was a national sport in US. Winning auctions at the last moment. So a lot of people were kind of just waiting until the last moment and just try to fire up. That's distributed systems at its best, really, right? Because it depends on so many things getting right to be able to submit your query at the last moment. And it's even a question of, OK, which one goes first? Does eBay have any delivery guarantees about if 100 people bid on the same item and in the last second they send a request, who gets to get the item at what price or whatever? Right? Nevertheless, eBay was in shambles because it was going up and down and up and down. And the attack on eBay was, in fact, an attack on the entry point, the router, the main router that distributes then the web request and does some sort of load balancing, which we will talk about in this class, so on and so forth. So single point of failure, even if it's in the form of some sort of a front-end router, could potentially be very problematic. Okay? Well, it turns out that it was something that could be exploited in Cisco routers. And it wasn't only eBay. I mean, Amazon was down a day or two. All the major websites were down because these guys discovered that you can dizzy up the routers in a certain way. How? That's distributed systems also. And we are going to talk about some of these exploits. In that particular situation, what was happening is they forced the router to reboot by forcing the router to commit resources and a large number of resources. So for every TCP/IP connection, the router has to keep track of the information on the TCP/IP connection and allocated a little bit of memory to keep track of some counters and whatnot. And what these guys were doing is simply opening an enormous number of TCP/IP connections. Actually not even opening them, just pretending they opened them. Just send the first package in the TCP/IP, a SYN. This was a SYN attack. It's a famous SYN attack. The SYN is the first packet in a TCP/IP protocol that says, I want to open a connection. And what they did is they took over many computers, transformed them into a wonderful distributed system that was just sending these SYN packets. By the way, that takes tremendous skill because in order to send those SYN packages, you have to be at the lowest level in the operating system to do something so low level. Because any high-level program would say open connection, and that would be the full open connection and do the whole hullabaloo, right? They had to take over something called raw sockets. So that essentially means if you understand how the transparency works in a system, you can get under the skin of the system and make it do things that are not transparent, that are very low level to achieve a certain goal, right? This is why maybe it's important to understand the magic that happens in distributed systems to know how the lower levels are used, because occasionally you do need to go very, very low level to achieve a certain thing, either for performance reasons or if you're into hacking to know how to hack, right, or something like that. I'm not going to teach that in this class, though, okay? So here's what we're going to do. On Tuesday, I'm going to finish this initial presentation for what distributed systems are to give you a broad overview what to keep your eyes on in the class, and start pointing out important issues about Scala, because I wanted to start working on the first project. I have a mailing list, which I forgot to mention. Everything happens through the mailing list. Sign up, right? It's on the syllabus. It's on the website. Sign up today. Anything I have to say, I'll throw it on the mailing list. The TAs are going to monitor the mailing list. I strongly encourage you to talk on the mailing list. You find a nice resource for Scala, put it on the mailing list so other people can use it. Do not share solutions to problems. Share know-how, share websites, right? I want all of you to collaborate through the mailing list to get good, all right? Okay, see you Tuesday.